everyone, today we are going to learn about the binomial theorem. And the binomial theorem connects two concepts that we have already learned about. It connects combinations with our special products. So special products are what we are going to do for our warm-up for today. Our warm-up for today will require you to use our special patterns for finding the products of binomials that are either being squared or cubed. Those special products, remember, are perfect square trinomials or Leal, or the 1-3-3-1 method. So what I would like you guys to please do is please go ahead and pause the video and try finding the product of these three problems using your special product rules or your special pattern rules. So go ahead and pause the video, and once you have come up with an answer, go ahead and start it up again, and we'll see how well you did. All right, hopefully you were able to try these problems on your own, and you were able to see that letter A is a perfect square trinomial. That means that we're going to take our first term and we're going to square it. Then we're going to take the product of our two terms, x times y, and double it. So that's going to be plus 2xy, plus your last term squared. So you should end up with x squared plus 2xy plus y squared. For letter B, this is considered a Leal problem, L-E-E-L, which we called that the 1-3-3-1 rule. And the 1-3-3-1 rule goes like this. For your first term, we first start off by writing out 1, leave a little bit of space, 3, leave a little bit of space, 3, and then a 1. Then with respect to our exponents, we are going to have 3, 2, 1, 0, then 0, 1, 2, 3. So those are our exponents of each of our terms. So let me zoom in a little bit for you guys. So my first term is x, and I'm going to take that x and I'm going to cube it. Plus, I'm going to take x and I'm going to square it. Then I'm going to take x and I'm going to raise it to the first power, and then I'm going to have x raised to the 0 power, which you don't even have to write, so I don't even think I'm going to write that, because anything to the 0 power is 1. Then you take your second term, which is a 1, and we have 0, 1, so this is going to be 1 to the first power, plus 1 to the second power, plus 1 to the third power. So now I'm going to work with each term individually, and I will end up with x to the third plus 3x squared plus 3x plus 1. And so that is your answer using the patterns of Leal, or the 1-3-3-1 rule. Let's go ahead and look at letter C. Letter C is a little bit more intense. We're still going to use the 1-3-3-1 rule. So I'm going to write a 1, leave it a little bit of space and write a 3, a little bit of space and write a 3, and a little bit of space and I'm going to write a 1. So my first term is 3x. So this is going to be 3x in parentheses to the third power. Then I'm going to write 3x to the second power, and then a 3x, and then I'm not going to write anything because that's going to be 3, 2, 1, 0 with respect to my exponents. And if you want to put a 1 right there, that's not a problem. When it comes to 2y, my exponents will go 0, 1, 2, 3. So I'm going to write nothing for the first term. I'm going to write a 2y for the second term, and then a 2y to the second power for the third term, and then a 2y to the third power for the fourth term. So now you guys can see that. And because my sign in the middle is a negative, that indicates that I'm going to alternate my signs. So we always start with a positive term, so this is positive, negative, positive, negative. So we alternate our signs, making sure our leading term is positive. Now I'm going to clean it up a little bit. 3 to the third power is 27, so this is 27x cubed, minus 3 to the second power is 9. 9 times 3 is 27, and 27 times 2, that is equal to 54. So that is 54x squared y, plus 2 squared is 4. 4 times 3 is 12. 12 times 3 is 36xy squared, minus 2 to the third power is 8. So that's going to be minus 8y cubed. we are going to be using, like I said, these patterns when it comes to Pascal's triangle, as well as working with the binomial theorem. So let's go ahead and hop right into Pascal's triangle. If you were to arrange NCR, so using our combinations, any NCR that you can think of in a triangular pattern, or if you were to arrange the values of NCR in a triangular pattern in which each row corresponds with the value of n, you get what is called the Pascal's triangle, which was named after the French mathematician Blaise Pascal. Now this Pascal's triangle you must memorize for your test. So I'm going to write that before I describe it. So you must make sure that you memorize Pascal's triangle through row 5. So let me go ahead and explain to you how to use Pascal's triangle. Let me zoom in really quick. So Pascal's triangle goes like this. So what we have here is we have combinations. So if we have 0 being n, 0 choose 0 is automatically the number 1. So now we have we have the 0 row, so this represents row 0. Then if we were to let n equals 1, 1 choose 0, that equals 1, and 1 combination choosing 1 is also equal to 1. So this is considered row 1. For n equals 2, that means that we are doing 2 combinations choosing 0, 2 combinations choosing 1, 2 combinations choosing 2. So we end up with 1, 2, 1 if we were to put that into our calculator. This represents row 2. Notice that we have the pattern 1, 2, 1. For n equals 3, we have 3 choosing 0, 3 choose 1, 3 choose 2, 3 choose 3. And the values, if you were to put that into your calculator, is our allele, 1, 3, 3, 1. And this represents row 3. For our fourth row, the same exact pattern occurs. We have 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. And if you were to put all of those values into your calculator, you'll end up with those values equaling 1, 4, 6, 4, 1. And this represents row 4. And then row 5, n is equal to 5. So we have 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. And if you were to put all of those values into your calculator, you will end up with the values being 1, 5, 10, 5, 1. And this represents row 5. So you might ask yourself, how on earth am I supposed to memorize this triangle? There's got to be some kind of pattern. And you're absolutely right, there is. So here are some clues for patterns for helping you to memorize this triangle. The first thing to note is that the first and last numbers in each row are the number 1. So if you start with a 1, you know that you're going to end your row with a 1. That's the first thing. The second thing to note is that every other number, or every number other than the number 1, is the sum of the closest 2 numbers in the row directly above it. So let me look at that. Let's look at that a little bit closer. So I said that the numbers directly, the sum of the closest 2 numbers, or every other number is the sum of the closest 2 numbers in the row directly above it. So let's go ahead and talk about that. So directly above the number 2 is 1 plus 1. 1 plus 1 is 2. The number directly above 3 is 1 plus 2. 1 plus 2 is 3. 2 plus 1 is 3. Let's look at the next row. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Let's look at the next row. 1 plus 4 is 5. 4 plus 6 is 10. 4 plus 6 is 10. 4 plus 1 is 5. So hopefully you are able to see what this pattern is. And we're going to use this a little bit more in just a second. So let's go ahead and look at example number 1. It says, out of 5 finalists, your class must choose 3 class representatives. Use Pascal's triangle. So they're specifically asking you to use Pascal's triangle to find the number of combinations of 3 students that can be chosen as representatives. So we have a total of 5 students. And we're talking about 5 students and a combination of 3 students from 5 finalists. So 5 choosing 3. So the way to figure out what we are going to be working with, well, this number right here represents your row. This represents row 5. And this 3 right here, the way that you can identify your number, this number represents your diagonal. So let me talk about diagonals in just a second. This represents diagonal number 3. All right, so let's go ahead and look at what we know. So in terms of row 5, diagonal number 3. So let's go ahead and identify our diagonals. So looking at Pascal's triangle, your first row of 1s, this represents diagonal 0 because this comes from row 0, diagonal 0. This next diagonal represents diagonal number 1. Corresponds with row 1, diagonal 1. The next diagonal is 2. The next diagonal is diagonal 3. The next one is diagonal 4. And finally, this is diagonal 5. Because this one would continue as more numbers just below it. So anytime you're working with only 1s, like right here, that's considered diagonal 1. So your answer for row 5, diagonal 3, so that's going to be right here, the answer is 10. So there's no real work for you to show other than to use Pascal's triangle. So the answer in this case is 10. And you're more than welcome to verify that that answer is correct by using our formula for combinations that we learned about in the last lesson. And that is 5 factorial divided by, well, 5 minus 3, that's going to be 2 factorial, times 3 factorial, which is equivalent to 5 times 4. I don't have to write 3 times 2 times 1 because that'll just cancel out, all over 2 times 1. So that is equal to 20 over 2, which is 10. So both approaches will still get you the right answer. But what we want to do is we want to make sure that we understand and we know how to use Pascal's triangle to get the right answer. So if you were to ask to come up with this answer using Pascal's triangle without using combinations, what I would recommend that you do once you have Pascal's triangle memorized is I would expect that you would write down the whole 5th row. So this would be 1, 5, 10, 10, 5, 1. So that's what I would expect you to write down. Knowing that the first one represents 0, we would go to diagonal 3. 1, 2, 3. There's your answer. So that's the work that I would be expecting you to show. I do not necessarily want you to show this work. However, it's a great way to verify your answer. All right, let's go ahead and look at example number 2. For example number 2, it says, from a collection of 7 baseball hats, you want to trade 3 of them. Use Pascal's triangle to find the number of combinations of 3 caps that can be traded. So we are talking about 7 choosing 3. So that means that we need to look at the 7th row, so row number 7, and diagonal number 3. That's what we're looking for. Well, I said that you only needed to memorize Pascal's triangle through number 5. And I'm not going to give you any rows, or not too many rows greater than 5. 7 is probably the maximum row that I'm going to be giving you. Maybe row 8 I might give you. But anyways, the way that you solve this using Pascal's triangle is this. You would write down what the 5th row is. And from the 5th row, you would be able to identify what the 6th row is. And then you'll be able to identify the 7th row using that sum trick that I showed you just a second ago. So let me make sure that this is in focus for you. It doesn't look like it's very clear. So here we go. Row number 5, we know, I'm going to leave about a finger of space because it's going to go in a diagonal. Remember that this is a triangle. And I'm going to write the number 1. So this is 1, 5, 10, 10, 5, and 1. Now I know that I'm going to be starting with the number 1, so I'm going to write a 1 right here. And I know that 1 plus 5, that is 6. 6 plus 5 is 15. 10 plus 10, that is 20. 10 plus 5 is 15. 5 plus 1 is 6. And I'm going to end my row with a 1. So next, I'm going to start with the number 1. 1 plus 6 is 7. 6 plus 15, that is equal to 21. 15 plus 20, that is 35. 20 plus 15 is 35. 15 plus 6 is 21. 6 plus 1 is 7. And I end my row with a 1. All right, now please make sure that you give yourself a little bit of space whenever you are creating your rows, because you don't want numbers to look like the number 17 or the number 71. You want to give some space so that you can actually see what those numbers are supposed to be. All right, so we want to look at row 7, diagonal 3. So remember that this is diagonal 0, diagonal 1, diagonal 2, diagonal 3. So row 7, diagonal 3, the answer is 35. So that is our answer. So that is how you use Pascal's triangle. And this is the work that I would expect you to show on your homework, as well as on any test or quiz that we have in here. So in terms of giving our answers some context, I forgot to give some context up here for example 1. Example 1, we would end up with 10 combinations of students. Or I'm going to say 10 combinations of representatives. And for this example down here, 35, we have 35 combinations of 3 hats. So please make sure that you get into the habit of using context or giving some kind of unit, some sort of explanation as to what your numbers represent. All right, so now let's go ahead and hop into the binomial theorem, connecting the information that we've already used. So this is where combinations and our special patterns, as well as Pascal's triangle, all come together, and that is with the binomial theorem. Now, the binomial theorem is based on raising a binomial to some kind of power, to the nth power. So it says that for any positive integer n, the binomial expansion of a plus b to the nth power is very, very complicated. It's where you're going to be doing multiple FOILs together. So I might give you a problem where I will ask you to take something like x plus 1 to the 8th power, which if you were to do this old-fashioned, that would mean that you would have to do a massive FOIL quite a few times. That would be x plus 1 times itself 8 times, which would take you a full page of work to do, which is not very fun. So how on earth would you show all of your work when it comes to a problem like this? Well, that's where Pascal's triangle comes into play, as well as the binomial theorem. So if I gave you something like this as like a massive FOIL, it would take, like I said, an entire page for you to do. Let me even make sure that I have enough parentheses. 1, 2, 3, 4, 5, 6, 7, 8. So I have a lot of products that I would have to keep track of all of the terms. It would be a pain in the side to do. So in order to solve a problem like this, we are going to use the binomial theorem, which means that the first thing you're going to do is you're going to write the coefficients of each term using the nth row of Pascal's triangle. So what I'm going to do is I'm going to talk about the steps and do example number 3 at the exact same time. So to write the coefficients of each term using the nth row of Pascal's triangle. For this problem, we have x plus 4 to the 5th power. This, whatever that power is, represents the row of Pascal's triangle that you're going to use. So in this case, n is equal to 5, which means we're going to use the 5th row of Pascal's triangle. So that means if you ever get stuck, you're always welcome to use combinations. This really means 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. So if you ever get stuck, you're always welcome to go back to combinations. 5 choose 0, that is equal to 1. So if we were to write out write out our entire fifth row, that would be 1, 5, 10, 10, 5, and 1. So that's your first step. You write down Pascal's triangle going from top to bottom. So you would write it out vertically. So that's the first thing that you do. You write out the coefficients using that nth term. Whatever the exponent is, that's going to be the row that you're going to be working with. Step 2, from top to bottom, vertically, include the first term of the binomial with each term using the expansion, expansion using exponents in decreasing order. So what this means is, just like we did right here where we had 3, 2, 1, 0, 0, 1, 2, 3 with respect to our exponents for our Lille problems, we're going to be doing the exact same thing for these types of problems. So we would take our first term, in this case it is x, and I'm going to multiply 1 times x to the 5th power. Then I'm going to multiply x to the 4th power for our second term. Then x to the 3rd power, then x to the 2nd power, then x to the 1st power, and then x to the 0 power. So I'm going in decreasing order or descending order with respect to my exponents, just like we did with our Lille problems. Then so that is step 2. Step 3, from top to bottom, I'm going to include the second term of the binomial with each term of the expansion using exponents in increasing order. So increasing order means I'm going to take 4 and I'm going to start with 0 and work my way up. So this is going to be times 4 to the 0 power, times 4 to the 1st power, times 4 to the 2nd power, times 4 to the 3rd power, times 4 to the 4th power, times 4 to the 5th power. Now, step 4 says to simplify the result of each product and add the terms together if the binomial is a sum. If the binomial is not a sum, then we are going to alternate the signs between the terms if you see a difference. So if you see a subtraction, just like we have down here for example number 4, or like we had in our warm-up for today, we're going to be alternating the signs. We always start with a positive sign, then negative, then positive, then negative. And continuing on just like that. So I'm going to write down all of our terms. So I have 1 times x to the 5th times 4 to the 0. Anything to the 0 power is 1. So my first term is x to the 5th. 5 times 4 is 20. So that's 20x to the 4th. 4 squared is 16. 16 times 10 is 160. So that's going to be 160 x to the 3rd. 4 to the 3rd is 64. 64 times 10 is 640. X to the 2nd power. 4 to the 4th power, that's 1208. 4 to the 4th power times 5, that's 1280. X. And then 4 to the 5th power, that is equal to 1024. And then x to the 0 power is just 1. So we have no x there. So now I'm going to write down my answer of x plus 4 to the 5th power. That is equal to x to the 5th power plus 20x to the 4th power plus 160x to the 3rd power plus 640x squared plus 1280 x plus 1024. So that is my expansion, my binomial expansion. So you write down every single term that you came up with using patterns to come up with your answer. Now, if you wanted to, you could absolutely multiply x plus 4 times itself 5 times, but like I said, you'll probably end up with a half a page of work, and that's not anything that anybody wants to be working with. That's a lot of work to do. We have one last example of this set of discussion notes, and here we go. So for this problem, it says use the binomial theorem to write the binomial expansion of 2m minus n to the 4th power. So this 4th power represents your n value, or the row that we're going to be working with. So this is the 4th row. So like I said, I want you to please make sure that you have Pascal's triangle memorized. Otherwise, you're more than welcome to use combinations, but that's a little bit more work for you to show. So this is going to be 4, choose 0, 4, choose 1, 4, choose 2, 4, choosing 3, 4, choosing 4. And those numbers are going to be 1, 4, 6, 4, 1. So those are the first set of numbers that we're going to write. Now I'm going to work with the first term, which is 2m. And I'm going to start with my exponent of 4 and decrease my exponents as I go. Please make sure that you use parentheses. That's where most kids make their biggest errors, is that they forget that they need to raise the number 2 to the 4th power, for example. So you want to make sure that you use parentheses if you're working with a term with more than one number or letter. So I'm going to write 2m to the 4th power times 2m to the 3rd power times 2m squared times 2m to the 1st power times 2m to the 0 power times, going straight down, I'm going to take my second term, which is n, and I'm going to raise n to the 0 power because we're going in increasing form. So I'm going to use my exponents backwards. So n to the 0 power times n to the 1st power times n to the 2nd power times n to the 3rd power times n to the 4th power. Now I'm going to come up with every single term by cleaning up my products. So 2 to the 4th power, that is equal to 16. So this is 16m to the 4th. Remember that any number or any term to the 0 power equals 1. So now I have 2 to the 3rd power. 2 to the 3rd power, that is equal to 8, and 8 times 4 is equal to 32. So this is 32m to the 3rd, n to the 1st. My next term, we have 2 squared, which is 4. 4 times 6 is 24. M squared, n squared. Now we have 2 to the 1st is 2. 2 times 4, that is 8. So 8m, n to the 3rd. And then finally, my last term, anything to the 0 power is 1. So I'm left with n to the 4th power. Now, because we have a minus sign in between my two terms, this indicates that I'm going to alternate the signs. So since we're going to alternate the signs, we always start off with a positive number. So I'm going to write 2m minus n to the 4th power. That is equal to my first term, which is 16m to the 4th power, minus 32m to the 3rd n plus 24m squared n squared minus 8m n to the 3rd plus n to the 4th. So I'm alternating my signs. It's okay if your last term is a positive. Like I said, we're alternating signs, and sometimes that does happen. So this is your answer. And that is the end of today's lesson. If you have any questions over anything, please feel free to send me an email. I'd love to hear whatever your questions are. Otherwise, I will see you tomorrow in class. Tomorrow's homework will not be from the book. It will be a packet worksheet, and it's going to give you more problems on permutations and combinations, as well as give you an opportunity to practice using the binomial theorem. So like I said, give me an email if you have any questions. Otherwise, I hope you have a wonderful day.